This next equation looks very similar to the cardioid that we just graphed in the previous video, but I want you to notice that two things have changed. One of them is going to alter the type of polar graph altogether, and one of them just changes the kind of symmetry we're going to be expecting. So I want you to notice that in the cardioids, which hopefully you've watched that video first, these two numbers would have been the same. So you would have had a 3 and a 3 or a 2 and a 2. And so now we've got shapes where these two numbers will be different. This time around we are going to graph something that's got cosine in it, which means we are going to expect it to have x-axis symmetry. And so what I want you to do is look at the table and notice that this table generates the upper half, or it looks like the upper half, depends on whether the numbers are positive or negative, but it generates either the upper or lower half of my picture. And so the rest is going to be the same as it was for cardioids. We need to generate, unfortunately, the entire table of values to draw this graph. So I'll get you started. You would do 3 minus 2 cosine of 0 degrees, and of course cosine of 0 degrees is 1. So you have 3 minus 2. So you get an answer of 1 at 0 degrees. Then 3 minus 2 cosine of 30 degrees. And cosine of 30 degrees is square root of 3 over 2, which, remember, I said it really doesn't matter if you estimate that at 0.8 or 0.9 or 0.85. It's going to graph basically the same. So I'm going to treat it like 0.9 because it is a little bit closer to that. And so 3 minus 2 times 0.9, which would be 1.8. So I get 1.2 at 30 degrees. And so now take a minute, pause it, and finish calculating the numbers in this table, please. Okay, so you should have paused it and finished filling in the remainder of the table. And once again, before I plot the points, I want to discuss one or two little things. The first is that you'll theoretically catch that you've made a mistake about which angles you choose. If you hadn't noticed the symmetry, if you notice that the numbers are repeating themselves, these trig values will have the same magnitude as these trig values, but they should always be the opposite so that you're not generating the same points over and over and over again. So if you get the same R value for a lot of your points, you probably did the wrong angles in your table because you didn't look at the symmetry or something like that. The other thing before I plot these points is I want you to notice that none of these numbers right here worked out to be zeros, and that is because these two numbers up here are different, so they're never going to add or subtract to equal 0. So I'm going to go ahead and plot the points. I've got 1 unit out towards 0 degrees, 1.2 units out towards 30 degrees, 2 units out towards 60 degrees, 3 towards 90. So as I spiral out, I'm also spiraling farther away. 4 units out towards 120, 4.8 units out towards 150, and then last but not least 5 units out. So these are my points, and once again, if I follow the curve that I've developed, this is what I've generated. So now I need to take those and I need to mirror image those across the x-axis. So this point's already on the x-axis right here. This point right here swings around. Sorry, I don't know what happened there. The graph accidentally got erased. So we had drawn the spiral out and we were in the process of swinging those points around. And so this point was on the x-axis. This point swings around to over here. This point right here swings around to over here. This one, which is 3 units up, is now going to go 3 units down. And then these, I would swing around in the other direction, but that's just my choice. and then there. And so what I've got is this. Now it looks like we've graphed basically the same thing as the cardoids, but we really haven't. There's some very subtle differences, and they're easier to spot the more disparity you see in the equations. So the first thing that I want you to notice about this graph that's different from before is that it is longer in one direction than it is in the other direction, and that is once again because of the disparity in these two numbers right here in the equation. It's going to make it look like essentially an ellipse with a dimple in it, or an oval instead of a circle. It's not going to be as perfectly round. And then the other thing is, of course, that that dimple does not go all the way down to the center, because you're never going to end up with an R value of 0 if these two numbers are not the same. So other than those subtle differences, cardoids, and these are what we call limacons, are basically the same thing. The process is the same. You're just looking for very subtle differences. And the farther apart these two numbers are, the more obvious that elliptical shape will be. So in summary, for the limacons, you're going to do the same thing that you would have done for the cardoids. You notice the type of equation. It's got two separate terms in both cases, here and here. There's no fractions or anything like that, so you know that it's one of these two types. Then you look at the fact that these two are now different numbers. So you can't have, even if it's a plus or a minus, you ignore the plus or minus. You're looking at the actual size of the numbers, and they cannot be the same to be a limacon. And then the rest is the same. If it's got cosine in it, it's going to be symmetric across the x-axis. And so the table of values you would need to do would generate the top half of the picture. You can always choose angles that would generate the bottom half, but you need to make sure you've gone all the way from the left side to the right side to generate either the top half or the bottom half. And then if it's got sine in the equation, it would have y-axis symmetry. So you choose angles that would generate either the left or the right half. It doesn't matter which ones. We just give you a standard set of angles and hope that it would make it easier so you don't have to think of that yourself. Now, the one thing that we didn't see this time around is we did not see a limacon with what we call a loop in the middle. And so the difference is, if I took my slightly elliptical shape and I had just, my dimple, that's the limacon we just drew. If I had a limacon that looked more like a black-eyed pea, so it had this loop on the inside of it, then that's generated by your A and B values. So go back and look at the one we just did. Our A value was 3 and our B value was 2. So the one we just did, our A value was 3 and our B value was 2. And so if you look at this, this is the situation we just did. The size of our A value was bigger than the size of our B value, and so we just had a dimple in ours. And so if they had switched, if this had been the 2 and this had been the 3, we would have had a loop. And so the only thing that would have changed is that when we draw our table of values, you're going to have all these points that go around, and then you'll have 1 or 2 points that look like they're inside of your curve. So when you start connecting the curve, you would connect this curve and you would connect that curve, and you would see I've actually got 2 loops, one big outer and one tiny little eye-sized loop in the middle. And that will be generated by your table of values. You don't have to go into it expecting it. That's it for limacons. I know they're very weird shapes. It's going to take practice. That's why we're giving you lots of time to practice in class next week. So come see us or ask us questions in class if you have problems.